All right, we're going to start this video by grading bonding chapter drawing day 1. Here we have Cl2 chlorine. It's 1 point for the answer, so you should have 14 available electrons. It's 2 points for the structure. Specifically, you should have 1 line connecting the 2 Cl's and then 6 dots on each Cl. It's 2 points all or nothing. Drawing a dipole or not drawing a dipole is worth 1 point. In this case, because it's nonpolar covalent, it is without a dipole. It's 1 point for the work here of subtracting these numbers and then 1 point for the answer. Moving on to the next one, which is N2. Here we have 10 total available electrons. When you distribute these electrons, you notice that neither N is happy, and so what you have to do is make multiple bonds. So it's 2 points for the structure. You should have a triple bond between the two ends, and then 1 lone pair on each end. It doesn't matter if they're on the top, bottom, or sides, okay? When you do the work for the polarity, it is nonpolar covalent, and you do not draw a dipole. Next one, we have what will be the structure for the H and SE? Well, SE has 6 and H has 1. Because SE wants a total of 8 and H can only have 2 at most, what happens is you're going to end up having 1 H on one side, 1 H on, and then another H on the other side. So it will form 2 H's and 1 SE. There should be 2 lone pairs on the SE. Structure is 2 points all or nothing. You don't draw a dipole because when you subtract the electronegativities, you get 0.35, which is nonpolar covalent. The next one, AsH3. This looks just like NH3 from the notes, and that should make sense because N is in the same family as As, which has 5 electrons. So you should have a total of 8 here. You have each H attached to the As and then 1 lone pair at the top of the As. It's 2 points all or nothing for the structure. It is nonpolar covalent, so you don't draw a dipole. This next one here, I want you to understand that it doesn't matter where you put the Cl's and the H's. What you should have, though, is 3 Cl's attached and 1 H attached. No lone pairs on the H, 3 lone pairs on each Cl, and they're all connected to the C's. When you are looking for your dipoles, right, there are no dipoles between the C and the H, so notice here how I didn't draw one, but then between the C and the Cl, you definitely have dipoles because those dipoles are pointing towards the most electronegative atom, which would be the Cl. For this last problem here, we have C2H2. You have a total of 10 electrons available. If you check to see if they were happy, you notice that neither carbon was happy. H's are happy because they're on the outside and they follow the duet rule. So then they had to share their electrons, and when they shared those electrons, they formed a triple bond. Once again, it doesn't matter if you drew them like in a U form or if you drew them as an N, right? Or if you didn't draw them straight across. The point is that you have to have a triple bond between the carbons, and then the hydrogen is single bonded to each carbon. When you figure out the difference in the electronegativities, you have 0.35, which is nonpolar covalent. So if you could please write your score out of 38. All right, and then what I would like for you to do is make sure that you have this for the next time that I see you. And then I will also look at your structures on Google Classroom, but you will have this score available for me to look at when I see you in class. So now what we're going to do is continue on with drawing day 2 notes. So we have first to look at bond strength and length. Bond length is the distance between the 2 bonding nuclei. So how long is the bond between 2 atoms in a molecule? And so what you have to know is that this image here is really going to help you to understand that concept. All right. So a single bond is much longer than a double bond, and then the double bond is longer than the triple bond. So here we can definitely see single bond is longer than the double than the triple. When it comes to bond dissociation energy, dissociation means to separate, right? It's the energy required to break the bond. The sum of the bond dissociation values in the amount of a chemical potential energy in a molecule. Bond strength is inversely proportional to the bond length. So a triple bond is the strongest, then the double bond, and then the single bond. So I like to represent that with these 3 rubber bands, right? So if I want to stretch one, right, rubber band, I can stretch it pretty far. So that would be, I'm using 1 rubber band, so that'd be the analogy of a single bond. But when I use 2, I can't stretch it as far, right? Assuming that I'm using the same force to separate them, right? And then 3, right, would be even less. It would take a lot more energy, right, to break all 3 rubber bands at the same time compared to just breaking 1. So that kind of gives you that analogy for bond dissociation energy. You definitely need to know bond length and bond dissociation energy for the test. Another definition you are responsible to know would be coordinate covalent bond. That is a bond in which one atom contributes both bonding electrons. So here's the idea. We know that carbon has 4 valence electrons and oxygen has 6 valence electrons. So if I drew carbon, that would have 4, right? And let's say I draw oxygen's electrons in a different color, right? We know that in order for the atoms to be happy, right, they're going to have to share their electrons. So these 2 would share, and these 2 would share. But the problem is that carbon still isn't happy because it has 1, 2, 3, 4, 5, 6. So then oxygen, right, we already know that they have to share the available electrons. We can't just create these electrons to be shared. So what's going to happen is the oxygen is going to just contribute a pair of its electrons into the molecule so that we can have stability, and the carbon and the oxygen are both sharing electrons, so they have 8 total. So what this structure actually looks like is it looks like this. It has a triple bond, right? And this triple bond forms, though, because it's a bond in which one atom contributes both bonding electrons. Oxygen has to give a pair of its electrons in order for both of the atoms to satisfy their octet. So how do we know if we have coordinate covalent bonds? Well, you have to draw them and see what happens, but it definitely happens a lot more with polyatomic ions and acids. So we already know what polyatomic ions are. We learned that in Chapter 7. They are structures that are covalently bonded atoms that have gained or lost electrons to become stable. If it's a polyatomic ion, all right, so if it's a polyatomic ion, remember that entire structure has an overall charge. So what we're going to do is put brackets and write the charge in the upper right hand corner. So I'm going to try to stay consistent and make sure that I use the same highlighter for showing polyatomic ions. So I'm going to use an orange highlighter. So this is a polyatomic ion, right? Polyatomic ion, we use brackets and we write the charge in the upper right hand corner. So I know that this is a polyatomic ion because there's a charge in the upper right hand corner. So how does that change what we learned the day before? The only difference is that the gain or loss of electrons has affected how we calculate the available electrons. to find the available electrons, like before, right? We're going to do the same thing. We look at the periodic table, so find the available electrons like before. Then we're going to subtract the charge to find the actual value. Just like how we did in chapter 4 when we figured out the number of electrons in an ion. We knew the mnemonic devices of ape, man. The atomic number is the same as protons as electrons, but we would circle the electrons because we always had to subtract the charge to figure out that value. So we're going to do the same thing here with cyanide. So we look at carbon, right? Carbon only has one atom, so we're going to take 1 times 4 because it has 4 valence electrons. Nitrogen, 1 times it has 5 valence electrons, so that's 5. So we get 9. And then what I have to do, right, is I have to take 9 and we subtract the charge. So now I'm going to take 9 minus a -1. And then I figure out what that is, which is 10. All right. So we know that this is a polyatomic ion. So I'm going to put brackets with the charge in the upper right-hand corner. So we know that every part of the structures that we draw are worth points. Putting the brackets in charge for a polyatomic ion is worth 1 point. So it's important that you include that. So now what I'm going to do is I'm going to draw my structure. I'm definitely going to draw my structure in pencil so that if I have to erase to have multiple bonds form, I can do that. So I have carbon. There's no central atom because there's only 2 things to attach. So I'm working with 10 electrons, right? So the first thing is I connect them. So 10 minus 2 is 8. I'm going to start on the left side. Fulfill the octet. So it's 1, 2, 3, 4, 5, 6, 7, 8. But how many did I use? 2, 4, 6. And I have 2 left. So I'm going to put those here. Now, I'm going to see who's happy. This carbon's happy. This nitrogen isn't. So remember, we have to work with the electrons that are already there. We can't put any more than what we started with, which would be 10, right? Like we can check here, 2, 4, 6, 8, 10. So I can see that carbon's happy. So what's carbon going to do? It's going to bring in its electrons to help nitrogen become happy. So I erase these, put those in here. Now I have a double bond. Carbon continues to be happy, but nitrogen only has 2, 4, 6. So I'm going to bring these in to here. So now what I have is this structure. Now the nitrogen has its 8, 2, 4, 6, 8, and both are happy. So this would be the structure of cyanide. Once again, this is a great example of a polyatomic ion. Polyatomic ions, you figure out the available just like how we did before, but we subtract the charge. We're going to make sure that we represent that structure correctly and we put it in brackets and put the charge in the upper hand corner. The next thing I'm going to teach you is resonance. It's not renaissance, it's resonance. Resonance structures are structures that occur when it's possible to draw 2 or more valid structures. So sometimes you can draw more than one structure and they have the same number of electron pairs for a molecular ion. This occurs when there's at least one multiple bond. Okay, so you have a double or a triple bond and one single bond. And all atoms attached to the central atom are the same. The atoms attached have to be the same. And what we do that's different about this is that we draw all structures connected by double-sided arrows. And that looks like this. Okay? So that is for resonance structures. So now there are 2 valid structures of nitrite, NO2 1-. So this example is a polyatomic, But what's new about this one is it also has resonance. Okay, so it has two new things. Remember, polyatomic ions, we just put bracket and charge. Now we're going to look at something that has a bracket and charge and it has resonance. So we're going to see what that means in this structure. So I see that it is a polyatomic ion, so I don't want to forget to do that. So I'm going to go ahead and put my brackets and charge in the upper right-hand corner. And I mean, if I had something like phosphate, PO4 3-, then I would be writing a 3- up here, okay? So now we're going to figure out our available. So nitrogen, there's only one. There's 5 valence electrons, so that's 5. Oxygen, there's 2 oxygens. 2 times the number of valence electrons, 6. That gives you 12. 5 plus 12 is 17. All right. Remember, what we do is we subtract the charge. -1. 17 minus a -1 gives us 18. One thing that students sometimes do is they forget to subtract the charge. We are not working with any problems that end up with odd values. So if you have an odd value, you probably did something wrong. Could you have an odd number of available electrons? Yes, but that has to deal with mostly exceptions that you'll see in AP Chem. All right, so now what we're going to do is draw our structure. I have NO2 1- because I only have one N and 2 O's. I'm going to put N as my central atom. Connect 2 O's. Okay, and then remember I have 18 to work with. So I'm going to put those up here. And when I connect them, 1, 2, 3, 4, I use 4. 18 minus 4 is 14. So now what I'm going to do is go ahead and add the electrons to the left side. 1, 2, 3, 4, 5, 6. I've used 6. I'm left with 8. 1, 2, 3, 4, 5, 6. I have 2 left. So I'm going to put the 2 there. So now I have 0 left. I put the last 2 here because this oxygen's already happy and this one's already happy. Now I have to check to see if everyone is happy though. I already checked these 2. Let's look at this N. 2, 4, 6. Not happy. So how do I know when I have resonance? This is where it's important for you to start looking at what the conditions are. So I know that these 2 are happy and this one isn't. When we say here that it has to have at least one multiple bond, it's actually always going to be a double bond, okay? Because it only works with a double bond. But here's the bigger thing that you have to see. These 2 O's are the same atom. And what can happen is either oxygen can give its electrons to make nitrogen happy. So let's say I take these 2 electrons and bring them in, right? So what that's going to do is make it look like this. So resonance, right, is when you have a multiple bond, a single bond, and all the atoms attached to the central atom are the same. Double, single, 2 things attached are the same. And here's why. Because I could have easily taken the electrons from this oxygen or this one. And when that's the case, I have to draw both structures. So this is resonance, okay? So I'm going to draw both structures connected by a double-sided arrow. I have to put polyatomics because it's still, or I still have to put brackets and charge because it's a polyatomic. But now what I have to do is show, right, that now the double bond is on the right side. And it's important to make sure your structures are correct, right? The single bonded O has 3 lone pairs. The double bonded O can only have 2 lone pairs. And then the nitrogen has 1 lone pair. Okay? So in this case, right, the double bond is between the first oxygen and the N. In this one, right, this structure, the double bond is between the N and the second O. Why do we have to draw this? Because it's if I were to look at the electrons in this structure, what I would actually see is that these electrons are actually jumping back and forth. They're almost like going back and forth here. If I were to look at the electrons in this atom, it would show that they're resonating back and forth. Resonating is to move back and forth in this movement, right? And so it almost looks like the cloud is going this way and then that way. And so we have to draw all structures when something has resonance. So now, if you were in class, I would have you practice with these two problems. So what I would like for you to do is pause the video and figure out the structures for SO3 2- and SO3. And then when you are done, go ahead and restart the video. All right, so hopefully you had enough time to do these structures. What you should have noticed is that this one had 26 available electrons, this one had 24. You should have also noticed that this is an example of a polyatomic ion. And this one was an example of one that has resonance. All right, so the first structure should look something like this. You have 3 oxygens that are single bonded to the S in the middle, right? And then the S has, right, the 2 electrons here, 1 lone pair, and hopefully, right, you put your brackets in charge, right, with a 2-. This does not have resonance because there's no double bond. This S is happy, 2, 4, 6, 8. This oxygen, happy, happy, happy. They're all happy. You didn't have to bring in any electrons from any of the oxygens that are attached. This one, though, is not a polyatomic ion, so I'm not going to put brackets in a charge. But this one has the electrons, right, resonating between the different oxygens. Now, it does not matter where you put the double bond first. What does matter is that when the oxygen is double bonded to the S, it can only have 2 lone pairs, and when it's single bonded, you should have 3 lone pairs. So make sure you drew those correctly. So in this one, it was between this oxygen on the left and then the S in the middle, right? So maybe I'll just go this direction, making sure that I put the correct number of electrons on each oxygen. And now I have to put the double bond at the top. This one can only have 2 lone pairs though, 3 lone pairs, and then 3 lone pairs. When I have resonance, I have to put the double-sided arrow between the structures. You have to draw all structures when it does have resonance. Okay? Last thing we're going to look at is non-octet structures. Remember, we talked about, actually, on the first day of notes, how there are some that are exceptions. We looked at this page where we said beryllium and boron are exceptions. And we said that they're exceptions because beryllium is actually a metal and boron is a metalloid. And this chapter deals with nonmetals. So we said that even though, right, they're not nonmetals, we will see them in molecules because they're so small and they can act like nonmetals to form the structures that make molecules of sharing of electrons. So here, beryllium is happy with 2, boron is happy with 3. What does that mean? If I see a beryllium, it's going to have 2 bonds. Boron, 3 bonds. Careful with the B's. You do not satisfy the octet with these, okay? So that's what we're going to look at now. Here, beryllium is stable with only 4 shared electrons, 2 bonds. Boron is happy with 6 shared electrons, 3 bonds, right? Do not follow the octet rule. So let's look at BeCl2. When I'm looking at BeCl2, I have Be, one of them, 2, gives us 2. Cl, there's 2 of them, 7 valence electrons, 14, that gives me 16. So I start with Be, 2 Cls, connect them, 2, 4, I have 12 left. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now I have 0. This Cl's happy, this Cl's happy, this Be only has 4. But it is happy because remember, it's happy with just 4 shared electrons. We don't add any more. Let's move on to this one because this is the next exception. Boron, right? Boron, 1 has 3 valence electrons which are available. So there's 3 there. H, 3 times 1, which is 3. I have a total of 6. B goes in the middle because there's only 1 of them. And H go on the outsides. Right? So I had 6, 2, 4, 6, 0 left, right? H is happy, and then I got to be careful with the B's. This does not follow the octet, so I know that this is also happy with just 3 bonds. Now the last one, expanded octets, more than an octet. Central atom has more than 4 bonds. So if I have something like PX5, PX6, or SX5, or SX6. This happens with phosphorus and sulfur only, okay? And so remember, I always like to tell you why something is an exception. It's going to help you to remember it even more, okay? If I look at phosphorus and sulfur, they're in the 3rd energy level, 1st, 2nd, 3rd. So because they're in the 3rd energy level, they have electrons that can go into the 3s, 3p, and the 3d. Even though the 3d aren't down until down here, right? They can go in there because they're in the 3rd energy level. And so because more electrons can fit down there, they can hold more electrons, okay? So when I'm looking at PCl5, what I have to do is just allow that central atom to have more than 4 bonds. So if there's 5 things attached, so this X would be some other atom, it's usually a halogen, I just connect them to the central atom. So this one also does not follow the octet rule. So technically all 3 of these do not follow the octet rule. So if I look at PCl5, P has 1 times 5, which is 5, Cl, which is 5 times 7, which is 35. That gives us a total of 40. I know that P goes in the middle, right? And so what happens is I just go ahead and put all 5 Cl's onto my P, right? And so now I had 40. Now I've already used 2, 4, 6, 8, 10. I have 30 left, right? And if I have 1, 2, 3, 4, 5 atoms, 30 divided by 5 gives us 6. Can 6 fit on each one? Yes. So you got to make sure you draw them. And then now I've used up all of them. All the Cl's are happy. And then the phosphorus, you might say, well, that has 2, 4, 6, 8, 10. But it's happy because it's an expanded octet, which means it can hold more than 8, okay? So here's an example of SF6, right? It has 6 things attached. It will still use all the available electrons, but you don't have to worry about any double bonds or triple bonds. You just connect them to the BE and the B's, and for the expanded octets, you just allow them to have more than 4 bonds. They're either going to have 5 or 6. So that concludes our notes for drawing day 2, but now we're going to look at the homework. So in the homework is two-sided. So I'm going to tell you the number of exceptions. So on this homework assignment, there are 4 exceptions. 1 on the front and 3 on the back. Some of these have resonance. You won't know until you draw them. Some of these are polyatomic ions, which means you need brackets and charge. So a page that I think is important for you to look at would be the page that has the information about how you're going to be graded. So make sure you look at this picture or this page. This is on page 4 of your notes. Structures are worth 2 points. If it has resonance, it's going to be worth 1 point for each resonant structure after the above structure that you were supposed to draw. Remember, not all structures have resonance, so don't start putting everything or don't start displaying resonance for every single structure. It's only when you have a double bond and a single bond, all the atoms attached are the same. This is for you including the double-sided arrows when the structures are drawn. Shape, we still haven't learned that yet, so that's not until day 3. So don't worry about that one yet. If it's a polyatomic ion, you're going to put brackets and charge. Dipoles are drawn when you have a polar molecule. In this homework assignment, though, I don't want you to worry about dipoles. We'll continue that again on day 4, okay? So homework is front and back. Please make sure you turn that in based on what it states on Google Classroom.